This topic is called ring resonators. One of the important problems of conventional integrated optical devices is the aspect ratio. So, the devices like the MZI, the directional coupler, the waveguides, these are all thin and long. Angles are very small, of the orders of a few degrees. So, due to this we are not able to use the chip area very effectively. So, if you take a typical conventional integrated optical devices, the cross section is of the orders of a few microns, say 50 microns, whereas the length is of the orders of several millimeters. So, due to this we are not able to use the chip area very effectively. One of the solutions for this is the ring resonators. In the ring resonator you have a waveguide in the form of a ring like this, and you have several bus waveguides. This is the straight waveguides are called the bus waveguides to launch light into and out of the ring resonator. So, there are many configurations, many variations and many applications. So, several of them are being shown here. For example, the double ring resonator, the triple ring coupled resonator, and here is an array of resonators coupled. The light is launched into this and then it can be tapped out across other ports. One of the important features of the ring resonator is the resonant frequency. As I will show in the next slide, it can operate only at a particular optical frequency. So, this is a frequency dependent device that provides a lot of applications and uses. The variation of this is called the racetrack resonator, where you have a long length for coupling between the ring and the waveguide. There is another important feature that you observe, that there is a straight waveguide and a curved waveguide or the circular waveguide coupled to the ring. It is not unlike the straight waveguide coupling that we have noted earlier. In the earlier directional coupler we had noted two waveguides which are close together but straight. In the case of ring resonator you have a curved waveguide. I will put it in a different way. You have a coupling between the straight waveguide and curved waveguide. That makes the mathematics more complicated. And you also see some of the typical ring resonators fabricated that appeared in the current literature. Typically they are of the orders of a few microns or a few tens of microns in the radius, and since many of these devices are silicon based, you know that the waveguide widths are of the orders of 0.5 micron and by 250 micron, etc. So, 500 nanometers by 250 nanometers typically the size. So, there are several applications that I am showing here. So, ring resonator has become a multifunctional device. You can use it for many purposes, like a directional coupler. We have noted that a directional coupler could be used as a power divider, as a switch, as a modulator and so on and so forth. So, similarly an integrated optical ring resonator could be used for various purposes. I have shown some examples here. One of the important applications is called the delay lines. It is very difficult to achieve delay on the chip because you have very small length. If you use gratings you have good amount of delay, and ring resonator is another important way to obtain a good delay line. This has applications in communications to correlate different signals, the recognition of the optical header in a communication link and so on and so forth. So, I will highlight another important sensors. You can make sensors out of the ring resonator, as I will show in one of the slides. You can also configure the arrays of rings for multiplexing and demultiplexing in a communication link. Then you can use it ultimately for quantum information functions. I have put here. You can also think of a ring resonator as a fundamental element building block for quantum information functions, which I am not highlighting here. So, and of course in one of the applications I will show you that we can configure it as a logic gates and so on. Next. So, this slide shows some basic properties of a integrated optical ring resonator. As I said earlier, you have a waveguide in the form of a ring coupled to a bus. They are not joined, but there is a small gap. The properties also depend on the radius, the gap, coupling and so on and so forth, the waveguide design, basic design, etc. So, you can use a simple geometrical optics approach to study the properties of a ring. I am showing here a ring with single bus, and there are electric fields E1, E2, E3, E4 in different sections of the ring resonator and the coupler together. So, the light could be coupled into the ring, comes back and couples back into the waveguide. A fraction of it can also go back, and iteratively there is a resonant phenomena in the ring. So, we can work out that the E2 by E1, the amount of the transmitted light, the spectrum of the transmitted light can be worked out in terms of the radius, in terms of the total length of the ring, the propagation constant or the effective refractive index of the ring waveguide and so on. And we observe a output characteristics like this for a ring resonator. On the x axis you find the operating wavelength, and on the y axis you have the field amplitude or normalized power. You observe that there are certain frequencies at which it resonates and a lot of power is extracted out of the ring. So, you have the expression for the wavelength, resonant wavelength given in terms of the refractive index of the waveguide and radius of the waveguide. This can be considered as effective refractive index of the waveguide. R is the reflection coefficient, T is the transmission coefficients, and you have what is called a field enhancement inside the ring, which is defined in terms of the field that is coupled into the ring with respect to the light that is launched. If more power is launched into the ring, then you can say that the field is much more enhanced because it goes round and round, and you can say that the total intensity of the field can be more than the one that is injected due to the concentration of the power. So, there are expressions for the field enhancement and field enhancement factor. You can look from the current literature, and this is an expression for the transmission coefficient as a function, field enhancement as a function of the transmission coefficient T. Similarly, you have several cases of operation of this device like the over coupled system, the critically coupled system and under coupled system and so on. So, these are further properties. Another important property of the resonator is the free spectral range, which is the distance between two resonant peaks, which could be given in terms of the operating wavelength divided by the effective index and the total length of the ring. So, you observe that with the radius of the ring, the free spectral range reduces. As you increase the radius, the free spectral range, the peaks get closer, which means, and for various technologies these values of the free spectral range are plotted here with the radius. Also the free spectral range reduces with different values of the operating wavelength. For different operating wavelengths you find the plot of free spectral range as a function of the radius. Similarly, the spectral width of the spectrum is very important. For many applications we need very sharp spectrum, and it can be given in terms of the difference in the wavelength between the, I will just show you. Suppose you have a peak like this, the 3 dB or full width at half maximum can be defined as the point where the field falls by half. So, this is a half power point, and this width at this point is the full width at half maximum. So, full width at half maximum can be given in terms of the radius and the other factors. So, closely related to the full width at half maximum is the quality factor, which can be defined in terms of reciprocal proportional to the reciprocal of the full width at half maximum. So, you have also the what is called the fineness of the spectrum, and also the variation. We can, there is a lifetime of photon in the ring. So, in a ring the photon is staying longer, which is an important function for delay applications, and you have the variation of the quality factor for various along with the various factors along the wavelength, along the transmission coefficient, and so on and so forth. Typical quality factors of the orders of the several thousands, and almost very little variation with respect to the wavelength. So, it is a very good feature that the device is broadband. So, this is an example of what is called a double ring resonator, double bus ring resonator. There are, this is a single bus configuration where the expression for the resonant frequency can be given like this, and there is a double ring where you launch the light into these, and you can use other ports E2, E3 or E4 to measure the output power. This is called the backward reflected port. You can observe this is one of the most common configurations, and so on. There are different coupling reflection coefficients or the coupling coefficients across each of these. You can also consider symmetric double ring, double bus ring, where both the couplings at this waveguide as well as at this waveguide are similar. So, these plot shows the output characteristics of a typical double bus ring resonator. Normalized power on the x axis and the wavelength on the other axis, they are quite sharp. So, at different ports the power output is shown here at throughput and drop ports. So, they are complementary. So, in the drop port it is a very sharp peak, and the throughput it is a dip. So, the ratio of the reflection coefficients is A in all these pictures. So, there are many applications. I am showing you a couple of applications to comb filter. So, you can design the rings to be of different radii and couple light across these resonators. There are many coupling points at each of these junctions. There is coupling from one ring to light power from one ring to the other, which could be very well utilized, exploited for making comb filters. Comb filter is a structure where it resonates at many frequencies, closely spaced frequencies. In this particular case, you observe a comb or the ring resonator of the radius of 21 microns, spacing that you can get for the spectral components as 1.37 nanometers, quite small. Of course, still smaller could be achieved by proper design, and it depends on the technology, etc. This is an example where you have half a nanometer as the channel spacing between the different spectral components. So, this is a first one is a characteristics of a side coupled ring structure. The side coupled in the sense you have coupling from the side and double sided coupled ring structure. So, there are peaks in between also here. 2 side coupled rings and 6 ring structure. This is a 6 ring structure. So, this is an example of a 16 channel demux or mux. You can configure the ring resonator such that you can achieve the function of a demux. A demux function has a function where you have light launched into the input port, could be tapped across each of the output ports at different wavelengths. By choosing the radii of these rings appropriately, you can get the peaks at different points, you can tap the signal at different points. Assuming all the spectral components or the channels are incident into the input waveguide, you can tap out each of them at the output points. There is an interesting feature that the light is coupled at this junction and at this junction, not exactly opposite ends. So, at the waveguides are placed perpendicular to that, and the coupling from this to the ring and from coupling is at that point. So, the expressions for the coupling coefficients are as shown earlier. So, this table shows the various properties with the channel number, the length, the radius of the ring, then the wavelength of operation that you can drop it, and FSR and FWHM and quality of each of these. So, from the picture you see that they are almost very uniformly distributed and have uniform attenuation. So, typical in this is the average full width at half maximum of about 0.62 nanometers and the quality factor of the orders of 180. This is quite small, but it could be achieved. You can achieve a very high quality factor by proper designs. So, this is an example of application of the ring resonator to a pressure sensor. We have seen the pressure sensor made on Maxent interferometer earlier, where you had etched out a diaphragm. You had earlier an interferometer like this, and on one of the arms of the interferometer below you etch out a diaphragm. In this case, from the mechanical analysis, the stress in variation is maximum on this waveguide, and so maximum change in the delta n, and the pressure output, optimum pressure output. So, in this particular example, we use a ring resonator where you have a diaphragm just below the ring, a circular diaphragm, so that the entire circumference can be utilized. So, on an analysis we will know that the stress is maximum at the boundaries. So, the refractive index change is maximum there, and so we can have a ring resonator based pressure sensor will be much more effective and utilizing the elasto-optic effect very effectively. So, you have the variation of pressure given by this expression, you have the effective refractive index of the waveguide, the coupling coefficient and the pressure on the right axis. So, you also have the thickness of the diaphragm, which is h, and also the radius of the ring. So, this picture shows the variation of the normalized stress along the radius of the diaphragm. So, you have delta n as a function of radius. So, you see that this is very low at this point at the center of the circle, and varying to a large values at the boundaries. This is only a refractive index as a function of normalized values. So, typical refractive index of the orders of 0.01. So, 1% change in the refractive index is much more than sufficient to achieve a very good sensing function. So, this is a plot which shows the variation of lambda as a function of pressure. So, when the pressure is incident uniformly on this ring, we can expect, due to the refractive index change, the resonant frequency is different. So, in this particular case I am showing a resonant frequency which is going down for application of a pressure of 100 kilopascals. When there is no pressure applied, you have a resonant frequency at this point 1.55005 and slightly less. So, this delta lambda phase shift is important factor which can be used to calibrate your sensor. You can plot delta lambda versus the incident pressure. You have delta lambda of the orders of a fraction of a nanometer, that is possible for pressures in the range of several hundreds of kilopascals. Wave shift is given by the free spectral range, and delta phi is a function of p, and typical radiuses are of the orders of a millimeter, quite large, and thickness of the orders of 6. This is a design which is designed for this range of pressure applications. So, the resonant wavelength shifts are of the orders of 8 picometer for kilopascal with a range of 30 kilopascals. So, there are several other applications. In the next topic on photonic bandgap structures, we will combine the properties of optical MEMS, the ring resonator and the photonic bandgap structures. Thank you very much for this module.